Okay, so in this question, we've been given a mass spectrum of a sample of zinc, and what we've been asked to do is to use that in conjunction with the other data provided to work out what the relative atomic mass of this particular sample is. And in this case, we're working with 3 different isotopes of zinc, 64, 68, and 70. And so let's just go through this. And we've been asked to give our answer to 2 decimal places, right? Okay, so first thing I'm going to do is actually match the relative isotopic masses with the bars on the actual graph. And how are we going to do that? Well, importantly, what we need to pay attention to is the mass charge ratio. So that's the x-axis here, so mz, mass charge ratio. And here, what we should notice is that it is close correspondence at the relevant numbers with what we're looking for. So at 64, we see there's one, there's a bar there. At 68, again, there's another bar. At 70, we see there's another one. So it's quite straightforward to match it in this case. So we've got 48. This one here is corresponding to this. I'm going to just color code it to make it a bit more straightforward to follow. 68. We've got one at 68, which is going to be corresponding to that. And if I just get another color, purple, so 70, right? So 70, we've got one at 70 here, right? So with that information, what I'm now going to do is take a look at, okay, well, we've got that, so let's see if we can actually use that to now work out the relative atomic mass. So okay, that's not erasing. I'm not sure why. Anyway, let's just go back to the pen. Okay, so what I'm going to use, I'm going to use this space over here to effectively work that out. Okay. So first of all, I'm going to take the 64, and so just to clarify, what we're doing here is taking each of the numbers and multiplying it with their relative abundances. Okay, so we're taking each of the relative isotopic masses and multiplying them by the respective relative abundances, which we've gotten from what we've got from the graph. So 64 here times 48 plus, and then we just change this to green, plus 68 times 11 plus, just change this to purple, 70 times 20. Okay, so that is going to give us effectively the first step, effectively, right? So once we do that, if you feel free to work that out on your calculator, but once we do that, what we're going to get is 5 to 20. Okay, so what do we do here at the next stage? Do we multiply this number? Do we divide it? What do we divide it by? Do we assume that the relative abundance total is 100. We divide it by 100. In this case, what as per principle, what we would first do is add up the relative abundances and find out what they add up to. So I'm going to just do that now. So I'm going to do 48 plus 11 plus 20. So if you work that out, see what you get at the end. Is it 100? It won't be 100 in this case. What we get is actually 79. And this is one of the reasons why it's so important to check, is because with relative abundances, you're not always gonna have it add up to be 100. Okay, so from this point, what do we need to do? Well, we need to take the 5220 and divide it by the 79. Okay, so do that now. And what do we get after we do that? So we effectively get quite a long number out of this. I mean, 66.0759449, and I mean, there's a bunch of other numbers. The next number in the sequence would be a 3, but I'm going to just leave it like this, right? I'm just going to round it to that. And effectively, what do we need to do with this number at this stage? Is this our answer? Now, if we just, by way of inspection, compare this number with the numbers in our question, as a rule of thumb, in a case like this, when we've got the range of isotopic masses, we'd expect that our answer, so I'm just going to scroll down so you can see this. We'd expect that our answer, this should be an A. This is not a 9, this is an A. Our answer should be greater than or equal to, and this is purely based on the isotopes provided in the question, it should be greater than or equal to 64, and it should be less than or equal to 70, right? So when we check our answer, it should be within this range. If it's somewhere outside of this range, given the numbers we've been provided, 64, 68, 70, we already know that probably we've made a mistake somewhere in our question. So what did we get? We got 66.075949. Now the question is, does this conform to our value of A, right? So would this still be true if that was equal to A? If that was equal to A, well, in this case the answer is yes, it would be still be true. So that's like just a visual inspection, just to error check along the way. However, the question again, is this our answer? We have to then refer to what the question specifies, the number of decimal places. If your answer has decimals, give it to 2 decimal places. This is what the question asks. We've got a number of decimal places, 1, 2, 3, 4, 5. We've got 6 decimal places in this particular case, as far as what I chose to write. So no, this isn't our answer, not quite. There's still another step, which is the rounding. right? And so if we round this, it's quite straightforward. We get, so round it to 2 decimal places, we're going to get 66.08. So far we've come up with a relative atomic mass of 66.08. Is this our answer? Well, it's within the range we would expect, and it's to 2 decimal places. So we can quite comfortably in this case say yes, this is our answer, 66.08. So that is the relative atomic mass in this case of our sample of zinc, based on the data provided. Okay.